Good day everyone! Welcome to the video tutorial about the trigonometric identities. First, what is an identity? An identity is an equation that is true for all values of variables. For example, the sum and difference of two cubes is equal to the quantity of x positive negative y multiplied by the quantity of x squared negative positive xy plus y squared. Another example is the product or square of a binomial, which is the square of the quantity of x positive negative y is equal to the x squared positive negative 2xy plus y squared.
Next, what are the 8 fundamental trigonometric functions? The first is reciprocal identities. Derive identities from the reciprocal values in the 6 trigonometric ratios. Derivation of reciprocal identities. Example, finding the reciprocal value of sine theta. Define it as y over r, cosecant theta as r over y. Define cosecant theta in terms of r, giving us y cosecant theta is equal to r. Substitute that value onto sine theta, which gives us sine theta is equal to y over y cosecant theta. Cancel like terms. This is y, and then we'll have sine theta is equal to 1 over cosecant theta. Next is finding the reciprocal value of cosine theta. Find it as x over r, secant theta as r over x. Define secant theta in terms of r. Then we'll have x secant theta is equal to r. Substitute that value onto cosine theta, which gives us cosine theta is equal to x over x secant theta. Cancel like terms, which is x, and then we'll have cosine theta is equal to 1 over secant theta. Here is the list of the reciprocal identities. Sine theta is equal to 1 over cosecant theta. Cosine theta is equal to 1 over secant theta. Tangent theta is equal to 1 over cotangent theta. Cosecant theta is equal to sine theta. Secant theta is equal to cosine theta. And cotangent theta is equal to 1 over tangent theta.
The next fundamental function is the quotient identity, which by definition is derived from the quotient of the values of the 6 trigonometric ratios. So how are these functions derived? If we would look back at the values of the 6 trigonometric ratios, which is derived from the unit circle, we would be able to manipulate its value to derive the quotient identity. To begin, we shall use sine theta, which is equal to y over r, and cosine theta, which has a value of x over r. In sine theta, if we would multiply both sides by r, then we would know that the value of y is equal to r sine theta, and the same process would go to the cosine value, where we would also multiply both sides by r to get the value of x, which is r cosine theta. One of the trigonometric identities is tangent theta, which is equal to x over y, where we can substitute the values of x and y to the ratio, giving it a value of r sine theta over r cosine theta, which can then be simplified to sine theta over cosine theta. The same process is done with cotangent theta, where we would also use the values of sine theta and cosine theta to derive it. This time around, the value of cotangent theta is equal to y over x. And if we substitute x and y, we would get r cosine theta over r sine theta, and if we would simplify it, we would get cosine theta over sine theta. From that derivation, we were able to determine the values of tangent theta, which is equal to sine theta over cosine theta, and cotangent theta, which is equal to cosine theta over sine theta.
Next, we have the Pythagorean identities. Since they are derived from the Pythagorean theorem, and it is placed within a unit circle, r could be replaced with 1. Given that sine theta could be expressed as y over 1 and cosine theta could be expressed as x over 1, since r is 1, we can substitute x and y for cosine and sine respectively, getting the final Pythagorean identity of cosine squared theta plus sine squared theta is equal to 1. From there, we could derive the other Pythagorean identities. First, by multiplying both sides of the equation by 1 over cosine squared theta, and then simplifying using other identities. Cosine squared theta over cosine squared theta would be equal to 1, and sine squared theta over cosine squared theta would be equal to tangent squared theta. And 1 times 1 over cosine squared theta would be equal to secant squared theta. So that's the second Pythagorean identity of 1 plus tan squared theta is equal to secant squared theta. The third and final Pythagorean identity, given cosine squared theta and plus sine squared theta is equal to 1, multiplying both sides of the equation by 1 over sine squared theta, and simplifying using other trigonometric identities of cosine squared theta over sine squared theta, resulting into cotangent squared theta, and sine squared theta over sine squared theta is equal to 1, and 1 over sine squared theta is equal to cosecant squared theta. So that is our final Pythagorean identity of cotangent squared theta plus 1 is equal to cosecant squared theta. Therefore, we have three Pythagorean identities. First, sine squared theta plus cosine squared theta is equal to 1. 1 plus tangent squared theta is equal to secant squared theta. And lastly, cotangent squared theta plus 1 is equal to cosecant squared theta.
So, after learning about the 8 fundamental trigonometric identities, we will now proceed improving trigonometric identities. So first, we have the given of tangent squared theta multiplied by the quantity of 1 plus cotangent squared theta is equal to secant squared theta. So we will be using the left-hand side to prove the right-hand side. We all know that 1 plus cotangent squared theta is a Pythagorean identity which is equal or congruent to cosecant squared theta. Therefore, we will substitute 1 plus cotangent squared theta as cosecant squared theta. We would have tangent squared theta multiplied by cosecant squared theta now. Now, let us remove and derive the tangent squared theta into sine squared theta over cosine squared theta multiplied by the quantity of 1 over sine squared theta, because the reciprocal identity of cosecant squared theta is 1 over sine squared theta. Let us now simplify the like terms, resulting to 1 over cosecant squared theta is equal to secant squared theta. We all know that 1 over cosecant squared theta is the reciprocal of secant squared theta. Therefore, substituting it, we would have secant squared theta equals secant squared theta. Therefore, it is equal. So, for the second given, we will have a more complicated one compared to our first given. Secant squared theta plus 2 tangent theta over cosine theta plus tangent squared theta is equal to 1 plus sine theta all over 1 minus sine theta. Since we will be using the right hand side to prove the left hand side, and there is no possible identity to change in the right hand side, we will be using the concept of conjugation. Through conjugation, we will produce a product of sum and difference, multiplying the denominator but its opposite side. So we will have 1 plus sine theta over 1 plus sine theta, and simplifying it, we will get 1 plus 2 sine theta plus sine squared theta all over 1 minus sine squared theta. We all know that cosine squared theta is equal to 1 minus sine squared theta, since derived from the original Pythagorean identity, cosine squared theta plus sine squared theta equals 1. So substituting it and distributing the cosine squared theta in each of the terms, we will get 1 over cosine squared theta plus 2 sine theta over cosine squared theta plus sine squared theta over cosine squared theta. So simplifying, 1 over cosine squared theta is a reciprocal identity of secant squared theta plus 2 sine theta over cosine theta. We'll just factor out cosine squared theta plus tangent squared theta, since sine squared theta over cosine squared theta are quotient identities. So we will get 2 tan theta over cosine theta in the second term by partnering 1 cosine theta and the numerator sine theta. So therefore, we prove that secant squared theta plus 2 tangent theta over cosine theta plus tangent squared theta is equal to 1 plus sine theta all over 1 minus sine theta.